Hello students, welcome to this module on nonlinear dynamics, which is part 2 in our series of modules on this topic, which is part of the course Introduction to Hydrodynamic Stability, CHE 614. Okay, in the previous module, we started understanding what is called a dynamical system. A dynamical system is nothing but a system of coupled nonlinear ordinary differential equations of the form dx1 dt is some function f of x1, x2, xn, let's call it f1, and similarly all the way up to dxn dt is equal to f of some other function fn of x1, x2, all the way up to xn. So these are in general nonlinear functions of the variables x1, x2. Okay, this is called a dynamical system. Now, if you note that the Navier-Stokes equations which describe fluid flow are partial differential equations in the sense that they have derivatives of various velocities with respect to spatial positions, and they also have products of various derivatives with respect to the velocities and the derivatives and so on. So they are nonlinear. So to understand the nature of instabilities and how things become unstable in Navier-Stokes equations, it is first useful to understand how things become unstable in a simpler context of what is called a dynamical system. Sometimes we can write this in vector notation. Dx dt is f of x. Okay. Now this system is called an autonomous system because the right side is the f's are the functions on the right side are independent of time. There is no explicit time dependence. I told you that if you have an explicit time dependence, such system of equations are called non-autonomous systems. And you can easily convert a non-autonomous system. In a non-autonomous system, you will have f vector x t, but you can convert a non-autonomous system can be converted to an autonomous system of one dimension higher by simply redefining time as one of the dependent variables. Okay, so you can call xn plus 1. If this is an n-dimensional system, you can call xn plus 1 as t, and you can rewrite this as dx1 n plus 1 by dt is 1, and you can add this to the system of differential equations. Now you'll get a modified system. You'll have a modified where this is now an n plus 1 dimensional vector, whereas the original x was an n-dimensional vector, and you will have a modified function, let's call it f tilde of x only. Now this x is also an n plus 1 dimensional vector which involves time. So you can always convert a non-autonomous system to an autonomous system of one order higher dimension. Okay. Now the solution of a nonlinear dynamical system is represented in what is called a phase space. A phase space is simply the phase space is simply the dimensions in which the space in which the various dependent variables form the various coordinate axes. If I take a three-dimensional system, okay, this is called a phase space. If I have a three-dimensional system, okay, now if you give some initial condition, in order to solve a system of ordinary differential equations, you need to define the initial conditions. The vector x at time t equal to 0 is some point in the n-dimensional or three-dimensional space, x naught. So this is that x naught. Now this x naught will of course evolve as a function of time as you solve this differential equation, okay, in some complicated fashion. Okay, and this is called the trajectory of the solution in the phase space. This is called a phase space trajectory. Okay. Now, in order to understand nonlinear systems, we first chose the simplest possible nonlinear system, which are 1D nonlinear systems. wherein it's an autonomous system, so you will have dx dt. The only dependent variable is x, is given by f of x. Okay. Now in this case, the phase space now becomes, in one-dimensional systems, a phase line, because in 1D there is only one variable x, and there is nothing much you can do. You can either go forward or go backward, unlike in three-dimensional space, where, as I've indicated here, you could go in any complicated path, that is not possible in 1D. Okay. So now, in order to understand the dynamics of how this trajectories flow in the line, it's useful to plot this graph, wherein I'm plotting x dot. By the way, dx dt is denoted as f x dot in nonlinear systems. So x dot is plotted against x. What is x dot? X dot is nothing but f of x. So basically I'm plotting f of x, and this is the phase line. The x-axis is the phase line. Okay, so let's take some arbitrarily shaped functions like this. Now the point at which x dot is 0, there the function f of x crosses 0, these are called fixed points, because x dot is 0 at these points. But x dot is f of x, so if x dot is 0, then f of x must be 0. So wherever f of x is 0, these are called fixed points, because the time derivative is 0. That is, once you go to this point, you cannot reach anywhere. You are just fixed there. Okay, you cannot move anywhere, because once you reach the position reaches there, then the time derivative becomes 0. So there is no further change. So in the language of transport phenomena or fluid mechanics, these are called steady states. Sometimes these are also called equilibrium points, depending on various disciplines of science. We use different jargon to represent the same idea, right? And here, okay, now so these are two fixed points. Now you can categorize the fixed points as being stable or unstable by looking at whether, if you move a little away from the fixed point, whether you will go back towards the same fixed point or you will fly away from that fixed point. Okay, now let's take this fixed point first. Okay, now let's take this fixed point. If I consider an initial condition sufficiently close to the fixed point here, now here dx dt is positive. That is, if I consider initial condition on this side, dx dt is positive. So all initial conditions to the left of the fixed point will move towards the fixed point. Now if I consider any initial condition to this side of this fixed point, then dx dt is negative, so x will decrease with time. So all initial conditions to the right, immediate right of the fixed point, will flow towards the fixed point, and similarly all initial conditions to the left of the fixed point will also go towards the fixed point. So this fixed point is called a stable fixed point. Why is it a stable fixed point? Because even small deviations will bring back the initial condition to the same fixed point, whereas this fixed point is an unstable fixed point. Okay, because if I take a little bit initial condition away, right, on to the left, then dx dt is negative, so x will continue to decrease with time. On the other hand, if I take an initial condition slightly to the right, dx dt is positive, so that is initial conditions x will increase with time. So these are the ideas of stable and unstable fixed points. So not all fixed points are stable. If I perturb the fixed point a little bit, sometimes the perturbations flow back to the fixed point, sometimes the perturbations take the solution away from the fixed point. Now if there is, so where will this solution go? Where will this initial condition go? Well, if there is nothing else here, it will fly off to infinity, because if there is another fixed point, then it will go to and settle to that fixed point. But in the simple graph that I have plotted, there are only two fixed points, so this is going to fly away to plus infinity. It will continue to increase. There is nothing to bring it back down. okay, to a fixed point. Now to understand this more quantitatively, we did what is called a linear stability analysis of this simple nonlinear equation. We said that x is equal to x star, which is the fixed point, plus a deviation, and then if I substitute this back, I'll get d eta dt on the left side, and if I Taylor expand f of x plus x star plus eta, I substitute x as x star plus eta. This is f of x star plus df by dx evaluated at x star times eta and so on. By definition, f of x star is 0. So what I will get is simply df dx evaluated at x star times eta. Okay. Now if I solve this equation, then I'll get eta of t is eta of time t equal to 0 times exponential of df by d eta at x star times t. So if this term is, if this coefficient that multiplies time is greater than 0, then it's unstable, because the deviation from the fixed point is going to fly away. It's going to increase exponentially. If it is less than 0, it is stable, because now the deviations are going to decay and you're going to go back to the same old fixed point. So this df dx at x star less than 0 stable, which is what we found from the linear stability analysis, is also borne out in this simple geometric picture. See, note the slope here is negative, okay, whereas the slope here is positive, so it's unstable. So this is stable. So now what else can happen in 1D? In 1D, if you think about it, the phase space is just a line. Okay, let me just draw without just a phase line. So there are many fixed points, right? And I may note that I'm going to denote stable fixed points as closed curves, sorry, closed dots, unstable fixed points as open dots. Okay, let's say you have things like this. Okay, now because this fixed point is unstable, things are going to go away. Okay, depending on where you start. Okay, if all these are unstable fixed points, open circles, and these are stable fixed points, right? So in 1D, what that different initial conditions will simply go. If the fixed point is stable, if you perturb a little bit away, it will come back to that same fixed point. If the fixed point is unstable, it will go away from that fixed point, unstable fixed point, and continue to float towards the nearest stable fixed point, neighboring fixed point. This is all that can happen in 1D. There is nothing much interesting in terms of the trajectories in phase line itself, right? Themselves. Now, there is, however, one interesting thing that happens even in 1D, wherein instead of dx dt is f of x, I'm going to introduce a parameter r. Okay, this parameter is like a parameter that can be varied experimentally if you wish. Okay, this is a parameter under your control. Okay, so this is for example, this is the Reynolds number in fluid mechanics. So you can increase the flow rate to change the Reynolds number. Similarly, this is an experimental knob that you have to change as per your wish. Now we want to understand how the steady states or fixed points and the qualitative structure of the flow changes as the parameter is changed. Okay, as r is varied, how does the flow by flow, I mean the trajectories in the phase line or phase space, how does the flow change? Okay, and how do the fixed points themselves change? That is, you may envisage a scenario wherein if I change the parameter, one fixed point that was stable could become unstable, or vice versa. So this subject, which deals with qualitative changes in the dynamics of a dynamical system, as a parameter is varied is called bifurcation. Bifurcations are qualitative changes in the dynamics. These are qualitative changes. Something dramatic happens in the dynamics as an external parameter is varied. Okay, and the parameters, the specific values of the parameters at which this change occurs are called bifurcation points. We'll see with, of course, many examples. Okay, right. So now let's now look at bifurcations. What we are going to discuss next is bifurcations in 1D. Okay, now let's there are 3 or 4 different qualitatively different bifurcations that happen in 1D. The first one that I'm going to discuss is called a saddle node bifurcation. Okay, what is a saddle node bifurcation? We will illustrate with this with the help of an example. X dot is equal to, this is the dynamical equation, r plus x squared. X dot, remember, is simply dx dt, and r is the parameter that we have under r control. Okay, now to understand, now r can be greater than 0, less than 0, equal to 0, whatever it is, right? It's a knob that we have. To understand the nature of flow, I will first plot x dot is equal to f of x as a function of x. Now first let's consider r is less than 0. Now remember, f of x is r plus x squared. Okay, so you will have a parabola. Now when r is less than 0, then you will have something like this. Okay, now there are 2 fixed points. There are 2 zero crossings of f, so there are 2 fixed points. Now we can categorize them as stable or unstable based on our criterion, geometric criterion. This is stable, this is unstable, because if I take any initial condition here, x is increasing with time, so the flow is in this direction. Whereas if I take any initial condition on this side, x is dx dt is negative, so x is decreasing with time. Similarly here, x is decreasing with time, x is increasing with time. So this is a stable fixed point, whereas this is an unstable fixed point. Okay, so this is r less than 0, and this is f dot is x dot is f of x. Now what is the idea of bifurcation? You want to of course understand how things change as a parameter is changed. So we will now consider r equal to 0. When r equal to 0, you will have a nice parabola. Sorry about this. I apologize for the quality of the figures. Okay, now again the fixed point is now when there is, this is f of x, x dot is f of x as a function of x. The fixed point is where f of x is 0, so the origin is the fixed point here. Now here the fixed point is a half stable fixed point, because on this side it becomes stable. So this is a half stable fixed point. This is r equal to 0. This is r less than 0, because here things are going to flow towards the origin, but if you are on this side, things are going to flow away from the origin. So imagine that as r is changed, as r is increased from something smaller than 0 towards 0, imagine this, as r is changed, these two fixed points are moving close to each other, and at r equal to 0, in some sense they are colliding. to give rise to only one fixed point. Now for r greater than 0, the parabola will look like this. Sorry, let's take this color. There is no zero crossing, and this means that for r greater than 0, if x is real, if we assume that x is a real number, real valued variable, there are no fixed points, because f of x has no zero crossings. Okay. Now we can summarize all this in a compact manner in what is known as a bifurcation diagram. I'll show this in the next page. So what we'll do, this is called a bifurcation diagram. What we'll do is that we will plot the solution, the fixed point that we get, x, as a function of the bifurcation parameter r. This is r equal to 0, this is r greater than 0, this is r less than 0. Now I'm going to plot the solutions, the two fixed points that we get at different values of r from this such a construction. You know that you can find these fixed points from here. You know also that the fixed point for x greater than 0 is unstable, whereas fixed points for x less than 0 is stable. So, and these two fixed points will merge at r equal to 0. So let's plot this qualitatively. So the unstable fixed point is denoted with a red dotted line. This is the stable fixed point. Okay. So how will you find those fixed points? We know that r plus x squared is 0. So x squared is equal to minus r. So for r negative, we can call r as minus alpha. So x squared becomes alpha. This is only for r negative, or x is equal to plus or minus root alpha, which is the magnitude of r. Right. So this is the plus solution. This is the positive solution. This is the negative solution out here. Now this is an unstable fixed point. So if I take any initial condition, it will flow away from the fixed point. Whereas this is a stable fixed point. So all initial conditions will, this is stable, whereas this is unstable. Right? So all initial conditions will go towards the stable fixed point. Now for r greater than 0, there are no solutions. Okay. So as I decrease r, there are no solutions. Suddenly solutions appear. So r equal to 0 is a point of bifurcation. Because for this model equation that we wrote down, as you imagine decreasing r, varying r in the sense of decreasing, right? Suddenly at r, there is no solution, but suddenly a solution appears at r equal to 0, and then there are two branches. There is an unstable branch and a stable branch. Okay. Right. So there are other names for this bifurcation. This is called a saddle node, or this is also known as the fold bifurcation, or this is also known as the turning point bifurcation. Okay, these are just names that you have to be aware of, but you should understand most importantly what is happening in this bifurcation. New solutions emerge as the parameter is varied. Okay, so you can also write this governing the model equation for a saddle node bifurcation. You can also write this as x dot is equal to r minus x squared instead of r plus x squared, and then the sense of everything will be opposite, right? And now this will become the unstable fixed point, this will become the stable fixed point. Okay, the negative will become the unstable and positive will become stable. And if I plot the bifurcation diagram, okay, it will appear like this: stable, unstable, this is R, this is X star. There is no solution on when R is less than 0. So things change just because of the change in sign, otherwise qualitatively everything is the same. Okay. Now if I look at this equation, x dot is R minus x squared, right? Now what are the steady states? What are the fixed points? Are obtained by saying that x dot is 0, x dot star is 0, or R minus x star squared is 0, or x star squared is R, and x star is plus or minus square root of R. Okay, these are the two solutions. Okay, so for R greater than 0. Now for R less than 0, if x is real, no solutions, because square root of a negative number becomes complex, and if you think that x is for real valued x. Okay. Now if you do a linear stability analysis, now we have to just find out what is f prime of x star. Okay, now x star is, let's say, plus root R. Now f prime of x star is minus 2 root R. So this is less than 0. So this is a stable fixed point. When x star is minus root R, f prime of x star is nothing but 2 root R, which is greater than 0. This is an unstable fixed point as per linear stability analysis, and that's what you will see here as well, right? In this particular case, this is a stable fixed point, this is an unstable fixed point. Okay. Now what if R equal to 0? Then f prime of x star is identically 0. Here linearization becomes invalid. Okay, because there is no first derivative of the function f at the fixed point. That means you cannot look at linear stability analysis for providing answers to the questions that we are asking. Now before I go to the next bifurcation, I want to mention what are called normal forms or canonical forms. Now the equations that we wrote, x dot is equal to R minus x squared, or x dot is equal to R plus x squared, are these the only ones that will exhibit saddle node bifurcations? The answer is obviously no. There are many nonlinear dynamical systems that can exhibit saddle node bifurcations. But the most important thing is that these are the simplest template equations that exhibit saddle node bifurcation. Okay. Now what I mean by that is, you may have, or these are in some sense the prototype equations. What I mean by this is that you may have a more complicated equation. For example, you may have an equation like this, okay, but close to the point of bifurcation, you will find that this equation can be expressed in this form. Now in this equation, this is a much more complicated equation. Bifurcation happens at R is equal to 1 and x equal to 0 in the XR plane. So if we Taylor expand this equation about x equal to x star equal to 0, okay, what you will find is that x dot is equal to R minus x minus 1 minus x plus x squared by 2 factorial, and so on. So this x will cancel with this x to give rise to x dot is equal to R minus 1 minus x squared by 2 factorial. So R is equal to 1 is the point of bifurcation, and if you look at this equation with this template, I can rename all this. I can call R minus 1 as some R prime, and I can absorb this factor of 2 also in the definition of the variable itself, and you will find that this is the same template as this. So in that sense, any saddle node bifurcation will locally near the point of bifurcation appear like this. Okay, that's why these are called normal forms or canonical forms. Okay, now the next bifurcation we are going to discuss is what is called a transcritical bifurcation. Okay, in saddle node bifurcation, as a parameter is varied, suddenly a solution appeared. Okay, suddenly solutions appear, of which one is stable and other is unstable. In transcritical bifurcation, there is always a solution. There are always two solutions, let's say in the simplest context, and one of which is stable, the other is unstable. As a parameter is varied, at the point of bifurcation, suddenly the nature of stability switches. The one which was stable earlier now becomes unstable, and the one which was unstable earlier now becomes stable. So let's understand this in the simplest context. The normal form for transcritical bifurcation is Rx minus x squared. Okay, so again we'll plot f of x. So this is f of x. I am plotting x dot is f of x as a function of x. This is r less than 0. There are two fixed points. This is unstable. This is stable. Now when r equal to 0, sorry about this. Okay, so you get a half fixed point, half stable fixed point. So this side is stable, this side is unstable. Okay, now for r greater than 0, so this is r equal to 0. Okay, when r is greater than 0, you will get okay, so now you get now this becomes unstable, whereas this becomes stable. I'm sorry about this. I have to just move this a little bit. I'll explain what I want to change by first okay. What I forgot to draw properly was that this is always x equal to 0. I mean x equal to 0 is always a fixed point. Whether it's stable or unstable depends on r. So here x equal to 0 was stable, half stable. Now for r greater than 0, x equal to 0 becomes unstable, whereas the other fixed point becomes stable. This is the hallmark of a transcritical bifurcation, so wherein you have two solutions. Let me draw them. So let me draw the stable solution with green color. Okay, so this is the stable solution. this is x equal to 0. Now let me also label this is x as a function of r. Now this is x equal to 0. This is the stable solution. Now the other solution, if you want to find what the two fixed points are, all you have to solve is rx minus x squared is 0 for fixed points. So x into r minus x is 0. So x is 0 and x star is equal to r. These are the two fixed points. Okay. Therefore, if you will see that I will denote unstable, sorry about this, with a line. Okay, so this is stable, this is unstable. For r less than 0, the x star is equal to 0 is a stable fixed point, x star is equal to r is the unstable fixed point. Okay, whereas r greater than 0, x star is equal to r becomes the stable fixed point, and x star is equal to 0 becomes the unstable fixed point. And the point of bifurcation is r equal to 0. Okay, so this is called a transcritical bifurcation, wherein there are two solutions, one stable and the other unstable. At the point of bifurcation, the solution which was unstable now becomes stable, and the solution which was stable now becomes unstable. Such a this is often referred to as in hydrodynamic stability, this is called exchange of instabilities. It's as if these two solutions are exchanging their nature at the point of bifurcation. So this is called exchange of instabilities. Okay. The next bifurcation we are going to discuss is called the pitchfork bifurcation. Okay. Here fixed points appear and disappear in symmetrical pairs as a parameter is varied. Now there are two types of pitchfork bifurcations. First, what we'll discuss is the supercritical pitchfork. What happens here is that if I plot the x dot versus x, now the model equation that represent that the canonical form for a supercritical bifurcation is given by this dynamical system: x dot is equal to rx minus x cubed. Okay. Now when r is less than 0, you have only one. The curve f of x will look like this. This is f of x. Okay. So I'm plotting f as usual. X dot is f of x as a function of x. So this is a stable fixed point, because if you draw the geometry construction, you will see immediately that this is a stable fixed point. Now at the origin, at r equal to 0, so the origin is the stable fixed point. When r is 0, then the origin becomes just weakly stable. It'll look like this. Okay, it's just about weakly stable. Whereas for r greater than 0, what you will find is that the origin becomes unstable, okay. It's something like this. This is f of x as a function of x. Now the origin is now an unstable fixed point, whereas two new fixed points emerge Okay, and the flow is like this. Two new stable fixed points emerge. Okay, so how do you find these stable fixed points? We have x dot is rx minus x cube. For steady states or fixed points, x dot is star is 0, is r x dot star, sorry, r x star minus x star cube. So if I take x star common, you'll get r minus x star squared is 0. There are two solutions, or rather there are three solutions. X star is 0. When r is greater than 0, there are three solutions. When r is so or x star squared is equal to r. So this has real solutions only for r greater than 0. Therefore, for r less than 0, there is only one solution. For r greater than 0, there are three solutions. X star is 0, x star is equal to plus root r, x star is equal to minus root r. Okay, so these are the three solutions. Now, so two new solutions emerge as you vary the bifurcation parameter in supercritical pitchfork bifurcation. So let's draw the bifurcation diagram. So what you will have is that you have a stable branch. Sorry about this. You have a stable branch which is x star is 0. This is what I'm plotting is x star as a function of r. X star is 0 is a stable fixed point. Now when r is greater than 0, you have two solutions, plus root r minus root r. Both are stable, whereas the original solution x star is 0 becomes now unstable. Okay, this is unstable, this is stable, this is stable, this is stable. Okay, so there is only one solution, one steady state for r less than 0, which becomes unstable at the point r equal to 0, but two new solutions emerge at the point of bifurcation. Okay, now and the original solution becomes unstable. Now we'll also discuss what is called a subcritical pitchfork bifurcation. Okay, wherein the model equation is quite similar, only the sign of x dot is rx. For supercritical you had minus x cube, for subcritical you have positive coefficient, means subcritical. Okay, so there are, what are the steady states, what are the fixed points? What you will do is x dot is 0 is x into r plus x squared. So x equal to 0 is always a solution. Now for r less than 0, in addition to x equal to 0, you also have x star is equal to plus or minus square root of minus r, or rather I can just say it as square root of mod r. Okay, r is negative. When r is positive, there is only one solution, x star is 0. Okay, so if I plot the bifurcation diagram, x star as a function of r, what I will find is that there are these two solutions, plus or minus square root of mod r. These are unstable solutions, they are linearly unstable. Okay, so what you will see is that there is a stable solution, which is x star is 0, which becomes unstable. There's no doubt that this solution has become unstable, but so this solution has become unstable. The original x star is equal to 0 solution has now become unstable, but two other solutions also are present for r less than 0, and they are unstable solutions. Okay, these are unstable solutions. Okay, the origin is stable for r less than 0, unstable for r, that is x star is 0 is stable for r less than 0, and unstable for r greater than 0. Okay, so the point is, what does this mean? This means that even though the system is unstable above r greater than 0, even below r equal to 0, right, there is a chance that because this solution is unstable, the flow is going to be like this towards the trivial solution. But there is also a chance that if you give a initial disturbance of sufficiently high magnitude, you may never see this original base state, original fixed point. You will fly off somewhere else. Okay, if there is nothing else, you will fly off to infinity. Usually what happens is there are some stabilizing terms. So remember, I have just kept these two terms, rx plus x cube. Suppose if there is another term, x dot is rx plus x cube minus x to the 5, okay, then this term has a negative sign, so this will act to stabilize. Okay, so what the bifurcation diagram is going to look like is the following. This is 0, this is r. Okay, now we drew all this before itself. Okay, now because of this stabilizing term, there is another stable branch. Okay, now this is anyway unstable, right? This is anyway unstable. This is stable. Okay, so let's call this rs. Okay, so when here there are no solutions, as you increase r, suddenly these solutions emerge. So these are saddle node bifurcations, which we will not focus here. We are more interested in this bifurcation, which is called the subcritical pitchfork. Okay, so now if you have for the same parameter r, it appears like you have this solution or even this stable solution. So if you do an experiment wherein you slowly increase r, carefully increase r, the path of the experiment will be like this. Now once you become unstable, once you are in the unstable region, you will no longer be able to realize this solution experimentally. So this is going to jump to this solution. Now imagine decreasing r very carefully. Now you will come all the way here, and then only you will jump to the x equal to 0 solution. That means that for a range of r between rs and 0, essentially, there is a possibility of two stable solutions. So if I change r, while increasing you may see this, while decreasing you may say this path. This is called hysteresis. Okay, now hysteresis is the lack of reversibility as a parameter is varied. Okay, now so depending on which steady state or which fixed point will be observed in experiment, it depends on the initial condition. If the initial conditions are such that you are below this unstable branch, then you will see only this solution. If you have a sufficiently large initial condition, you will see this. So but once you are here, and if you continue R very slowly, you decrease R slowly, you will continue to stay on this until there is no possibility of maintaining this solution. Therefore you will again go back to the zero solution. Okay, this is called hysteresis, and this is a hallmark of subcritical bifurcations. Why is it subcritical? Because it happens, the critical point for bifurcation is R equal to 0, and all interesting phenomena happen for R less than 0, which is why it's called a subcritical bifurcation. Okay, so I'll stop here and we'll continue with what is called the Hopf bifurcation in the next module. Thank you.